All right, what do we say for number one? Linear.
Linear.
How about number two? Exponential. Number three? Exponential. That's the of the previous year's population, 9/7 of. Now, if it were saying that it was, let's say, increasing at a rate of 9/7 of an alligator per year, I guess that, I mean, it would be a weird way of saying it, but that would be linear.
The population increase with another 1 and then 2/7 of an alligator.
Yeah, I mean, anything more than 0 alligators is too much for me, so. How's about number 4? Linear. And number 5? Exponential.
Wait, why is it exponential?
Because it's the same thing as the 9/7.
So whenever it's a fraction, it's exponential.
A fraction of.
But if it's like a constant rate of
Okay.
All right, so we're going to generalize our understanding here because contextually, you know, sometimes it's hit or miss, but if you have kind of a little bit of a recipe to analyze particular situations, then it becomes a little easier to diagnose what's what. So exponential growth model, y equals a times 1 plus r to the t power. The a value represents your initial amount. All right, or your starting amount, however you want to say it, but it's an amount, it's a quantity. All right, R is the rate of growth or decay. In decimal form. All right, so that's a pretty important piece of information, the in decimal form, because some problems will say, like in example 2, 1.5% per year, we would not replace R with 1.5. What would we replace it with? What's the decimal form of 1.5?
0.015.
Yep, good stuff, good stuff. Wizardry. Time determined, oops, that is not my scrolling device. Time determined by the units in the rate. All right, so time could be measured in days, weeks, months, millennia, nanoseconds. It all depends on the context of the situation, but a good way to get a clue as to what that unit of time would be to look at the rate that they give you in the problem. They'll always tell you what the units of time are because the rate will be given as something per something else. That per something will be time. All right, so the first example, a 3-bedroom house in Exponential City was purchased for $190,000. If housing prices are expected to increase 1.8% annually in that town, write an equation that models the price of the house in T years, okay? So annually and years go hand in hand. So we now have a sense of the units associated with time. Using your answer, find the price of the house in 5 years. So we'll worry about that in a sec. But we want to identify our 3 key ingredients, the A value, the R value, and the T value. All right, the A value is the initial amount. Well, they really only gave us one amount in this problem, right? Lovely. Somebody want to crack a window? Oh, okay. Well, my bad. The rate in decimal form would be what?
0.018.
0.018.
What?
All right. Ultimately, we're looking for the price after 5 years. So I'll make a note that time t is equal to 5. But the first thing that they wanted us to do was to leave t variable, write an equation that models the price of the house in t years. All right. So y would be equal to 190,000. One more zero. Times 1 plus 0.018 to the t power, all right? That's to address the first part of the problem. Not always a necessary step. We're only doing it here because they asked us to. They said in t years. Write an equation that models the price of the house in t years. Now, they're telling us as a follow-up, they're telling us to determine what the amount or the price of the house would be after 5 years. That's the point where we plug in the 5. All right, so the goal behind this kind of question is to get you to demonstrate that you know how to write an equation in general form, and then also that you know how to solve a particular equation. All right. More importantly, I think, anyway, because that's what their goal is. My goal for something like this is to demonstrate to you that you can come up with a model that'll give you the price of the house for any time t. All right, so they're asking us about 5 years from now, but you know, like you're probably too young for this, but have you ever heard the word mortgage?
Yeah.
Okay. Do you know what it is? Rocket mortgage, of course. Do you know what it is?
Isn't it almost like financing a house?
Financing a house, yeah. You're taking out a loan to buy a house. Does anybody, this is the big question, does anybody know the typical length of repayment on a mortgage?
15 years.
There's 15 years, that's one of them. 30 years is the most popular one. All right, so if I wanted to, for example, buy a house for $190,000, take out a mortgage to pay off that house, and then at the end of the mortgage sell my house, I might not care what its value is after 5 years. I might care what the value is after 30 years, right? Maybe, and this is even more important, maybe I would want to know what the best time would be to sell that house to make the most on a return, all right? So I would be thinking, all right, well, let me go the other way, and instead of determining what the price would be after 5 years, let me determine what number of years it would take for me to sell a house at a value of, let's say, $500,000, because maybe I want to buy a better house. All right, so I would want to determine how long it would take for my house to appreciate to a value of $500,000, so that I could sell it and then buy a new house. All right, with that accumulated value. All right, the blue equation will help me do that. This, you know, just plugging these values into a calculator and just crunching it, that doesn't really do much for you other than telling you what the value is at a particular moment in time. The blue one allows you to solve it for a desired quantity. All right, so really valuable stuff. So I talked a lot without doing any math, so let me do that. My TV for some reason is broken. I know that's music to a lot of your ears. Yeah, I know, it's going strong for 30 years, so.
30 years. I would one of those TVs in my house.
Let's see, rounding instructions? No? All right, we'll always be mindful of rounding instructions, but in this case, we're talking about money, so it would make sense to round to the nearest cent. Chuck a little $sign in there. All right, so after 5 years, this $190,000 house will be worth almost $210,000. All right, so that's in a good market, because it's for the last decade or so, it's been going the other way. Financial crisis, things like that. All right. A rare coin appreciates. So appreciates another word for increasing in value at a rate of 5.2% a year. If the initial value of the coin is $500, after how many years will its value cross the $300 mark, or $3,000 mark? Show the function that will model the value of the coin after t years. All right, so it's asking the same thing, but in a reverse order. Ultimately, as long as I have the correct information in there, I'm going to be fine. All right, so we have an initial amount. Starts off being worth $500. Its rate of increase is what? 0.052. All right, t ultimately is unknown, right? How many years will it take to cross the $3,000 mark? All right, so I want to sell this thing. I want to see what I can make off of it. You think like, you catch, I don't know. You guys know who, like A-Rod and Barry Bonds, like those guys? Like, yeah. Okay, cool. So I'm not too old. I'm getting there. Like if I said Mark McGuire, it's like barely, right? It's borderline. That's like the threshold. Right. Well, like, so you're at a baseball game and you're in home run territory, and A-Rod's up to bat and he just cracks his 700 home run, and you're lucky enough to catch it. It's already worth a ton of money, but it's going to increase in value. As long as you take care of it, it's going to increase in value over time. Right? Now, those things, there are measurables associated with that.
Waiting for time baseball. Probably won't increase, I don't know.
You should look it up.
Maybe I should.
Yeah? It's going to be worth more than you think. So, see, I have a Curtis Granderson autographed baseball. Now, I like him very, very much. I don't know that it's worth that much money. Whitey Ford is definitely worth.
Well, I bought that from like one of those, I don't know, but
like one of those shops?
Yeah.
Or did you get it from like a yard sale?
No, I didn't get it from the yard.
No, because yard sale is where you get the steals. Because the people are like, oh, this is my grandson's. I don't even know what it is. Here, you want it? Give me a cool nickel for it. And then you sell it for $13 million the next week, So, and then you give her a nice car or something for her troubles. And then she sues you for the other $12.5 million. So, anyway, we have y equals 500 times 1 plus 0.052 to the t power. Now, just a quick thought, because I didn't write this in the last one, but it's something that you might want to consider. It's the tiniest little time saver, and it's worth it. So this is the function that we have and the one that we need in order to determine the solution. But when we put it in the calculator, I would never write it this way. I would write it as 500 times 1.052 to the t power. All right, because it's very easy to do the addition of 1 and 0.052. You're just putting them together and dropping the plus sign. It seems stupid, but the act of not having to write this, it just feels like you're saving a lot of time. Also, this leads to a greater degree of understanding of what we were doing before. You know how when we were talking about doubling, you take the penny and you double it over a course of 15 days? You start to understand where that 2 came from. All right, we were actually using the same function when you double something, I mean, if you were to double your own height, for example, what rate are you increasing your height by?
1.5.
Not 1.5.
0.5.
Not 0.5 either.
1.
1. You're increasing it by 100%. All right? You're taking 100% of your height and adding it on top of your original height. All right? So if I go back to that original function, the original model, let's say, well, what am I, 65 inches? 65 inches. I want to double my height. Or let's say I double my height every year. That would be pretty cool. Actually, it would be terrible. I wouldn't even be able to fit in a room by next year. Whatever, it's a bad idea. So I would put in a 1 here for R. That would make my multiplier, 2. All right? If I wanted to triple, what percent increase am I talking about? So if I wanted to take my height and triple it, what percentage am I increasing my height by?
300.
No, that's what I'm getting to. I'm starting off with 100% of myself. I'm increasing by 200%. All right? So 1 plus 2 gives me a result of 3. That 1 is already built in there. This is what you're increasing the 100% by. All right? So here, we're taking 100% of the value of 500 and increasing by 5.2%. So take that into the real world. You're at a restaurant and you need to factor in a tip. So you take the bill, what do you multiply it by? 20%? Okay, instead of doing that, because that'll tell you what the tip is, I want to know how much that I'm going to have to pay, right? It's cool to know how much I'm actually tipping in dollar amount, but I want to know how much I'm going to end up paying in total, bill plus tip. So what should I multiply my bill by? 1.20. All right? So if you're going the other way, if you have like a sale, like 25% off. So an item costs $100, you know what it's going to be pretty easily, right? But let's say the item costs $72 and you want 75% off of that bill. Well, I'm sorry, 25% off of the bill. 75% would be crazy. What you're going to do is multiply by 0.75 because you're taking 1 and subtracting the 0.25 from it. All right? So these are like the real life connections. These are things that you do in everyday life without realizing it. All right? It's pretty cool stuff. Now, in terms of solving this, because it is asking, how many years will it take to cross the $3,000 mark? This is a calculator problem. Specifically, this is a job for the solver. There are other ways to do it, but if you were to do it with a graph and the intersection function, you'd have to find a window. So 35.345 years. And like I said, I'll post the video onto this after, when I'm sitting here like a schmo during period 4. All right, so we have 500 times, well, I already forgot, 1.052? Yes. Oh, so I didn't forget. That's wonderful. Raised to the x power, because you can't put a t in this. All right, we want that to be equal to 3,000. All right, so the first technique is the solver method. We've been doing this for the last few days, so you should be getting more and more comfortable with it. Math. I just like hitting the up arrow because it's the very last entry. Again, it's solver or numeric solver. It's one or the other. All right? Some calculators say one, some calculators say the other. Now we have our calculator set up, y1 and y2. If you don't have them set up, it's alpha trace to get y1 and y2. Alpha trace, enter for y1, alpha trace, hit the down arrow to get y2. All right, hit the down arrow. This is an answer for a problem that I did in a different class. It doesn't really matter what your answer is, because what you're going to do, because what we're looking at is the intersection, there's only ever going to be one intersection between a horizontal line and an exponential function. Right? So no matter where I start my x value, because this, if you really think of this, they call it an initial guess. It doesn't sound very mathematically precise, but that's what they call it in the calculator handbook, whatever it is. So it really doesn't, in a lot of cases, matter what number you put in here. This is where the calculator starts its search for the final answer. So I'm just going to leave it at that and hit alpha, enter, and it's going to drag me to the correct answer. All right, so it's telling me that it's going to take 35.345 years, I think. I got to go back to the problem in a sec, but it's going to take 35.345 units of time, whatever the units of time were, to determine or to get to $3,000 in value. All right. So when you have collectibles, it does make sense that you'd have to hold on to them for a long period of time. Otherwise, there'd be like a stock market type trading facility for that sort of thing, where people are like buying and selling within days of one another. That doesn't really happen. All right, second technique is the intersection function. If you like this method, you may not have to do it the other way. Just bear in mind, there are some questions that require you to graph exponential functions anyway. So if that's the case, you might end up having to do this. All right, so I would type in my function. First, I take note of what the scale of the function is. I have a y value that's as large as 3,000, which means that I need to have y values in my graph that go as large as 3,000. In terms of the x values, I really have no idea, right? But this is a nifty little trick that allows you to get the x values and the y values just by knowing one of the bounds. So I'm going to hit Window. I'm going to type in what I know, and that is that the y values need to go from 0, and I want it to go a little bit higher than 3,000, because if I only go up to 3,000, then that horizontal line is going to be right at the top of the screen. I don't want that. I want a little bit of space above it. So you can go to 3,500, you can go to 5,000 if you want it to be more in the center of the screen. Just pick a number that you know is bigger than 3,000. So I'm going to go to 5,000. Now for the x min and x max, you have a choice here. One technique would be to try to do a zoom fit. So go to x min or x max and hit, I'll go over this again in a sec, clear, zoom 0, and see what happens. Because again, all we're looking for is an intersection. If you get an intersection between the two graphs, then you've done your part. If not, then you didn't. All right, so that didn't work. But sometimes you get lucky. A zoom fit sometimes gets it done. All right, so instead of that, because it created a y min of 301 and it changed my y max to 3,000. I don't like that. All right, so sometimes it gets the job done, sometimes it doesn't. We do know that time starts at 0. This is more of a trial and error approach. All right. We already know what the answer is, but I'm going to pretend I don't. All right. I'm going to stay at 10 for a sec. Take a look at the picture. You see that the exponential function is trending upwards, and we have a horizontal line that's, well, horizontal line. It's a level line. So this blue line is getting ever closer to the red line, but not. I mean, we're not there yet. I'm only on the scale of 0 to 10. So that tells me that if I go out further in the x direction, I'll get closer to the red line. It's just a question of how much further in the x direction. So maybe I'll go to 20. By the way, if this doesn't sell you on the solver, I don't know what will. Oh, we're closer. But maybe you get a little impatient. Let's go to 100. As long as you can show a clear intersection on your screen, you'll have what you need. Ah, there it is. Got there eventually. All right, I have a clear intersection. So now what I want to do is find that intersection. Does anybody remember how to get to the intersection function on the calculator? Second trace. And it's the one that says intersect. Then the way I like to handle it is I just go right to the, going the other way. I try to get as close as I can to that intersection. And then what do? Enter 3 times. And so we get the same answer, right? This took it seemed like a day and a half to get it this way, whereas the solver did it in like a second. So, I mean, if that's not your motivation to use the solver, I don't know what it is. You know, and at this point, you don't have the skill the money that you deposit. All right. So we're assuming that you're getting interest on a period of 1 time per year. All right. So on an annual basis. Right. So what happens is, over a period of 1 year, you earn interest. So they're accruing value to award you at the end of the year. So it's basically, if you think of a savings as you loaning money to a bank. So whereas if you borrowed money from a bank, you'd have to pay them interest. If you have a savings account, you're loaning money to the bank, they're borrowing from you, they're paying you interest. Right? At the end of the year, they give you that interest. And then in the second year, you start earning interest not only on the initial amount of money that you invested, but also the interest that you earned in that first year. All right, so you earn interest on more money in the second year, and then subsequently in the following year, and it compounds upon itself. Right, so conceptually, it's a little dicey, but in terms of the process, it's not difficult at all because we're using the same formula. The exception is T is always represented by time in years. All right, so it's still A equals P times 1 plus R to the T. I mean, that's the annualized version of the formula, right? Because, you know, you might be asking yourself the question, well, what happens if you earn interest on a daily basis or on a weekly basis or a monthly basis? This is specifically related to earning interest on an annual basis, meaning you earn the interest throughout the course of the year. You don't get it until the end of the year. All right, so if you were to take your money out of the account, let's say in September, you deposit it in January, but you take it out in September, you get no interest. You have to wait to the following January to get that interest. All right, that's what this means. All right, but the problems are virtually the same. Ben's got $500. There's an interest rate associated with it. How much is he going to have at the end of the 5 years? So the A value, oh, sorry. I used a different version of the formula. I don't know why I laughed about that. There's nothing funny about that. I mean, I'm laughing because I'm me. And I find every idiotic thing I do to be funny. So, bless.
Thank you.
The reason why I wrote the other formula is because that's what the real accounting formula is. This is the math class version of that formula. So anyway, we're starting off with an initial amount of 500. We have 6% compounded annually, and we want to know what's going to be in there after 5 years. So y equals, and they're not asking us, oh, as 6 months and 5 years, so sorry about that. So if time is in years, what is 6 months really?
0.5.
0.5 years. So we need 0.5 and 5 years. So 2 calculations. All right, so what I would do actually, they didn't ask us to write the function. I would actually write the function in terms of time. Y equals 500 times 1.06 to the t, because again, the 1 plus 0.06 is the same as 1.06.
What? Oh, okay, never mind.
And then in your calculator, just go either to the table or evaluate it for these values. All right, so that you can write the function once, but get the answer pretty quickly. So we're talking 514.78. All right.
The last one is 1 or 12.
Okay, so yeah, your homework is just through page 18. It's just more of the same. It's a lot of practice with this. Next week I'll talk to you about how we're going to handle the rest of the year, because as you know, it's May, and yeah, we have a Regents exam coming up. So we got this year. It's middle of June. So we're looking at an assessment for this unit, one more unit, both of which are fairly quick, not rushed, but quick. And then we're hoping to have at least 2 weeks of review for the exam. But I'll start talking about after school review schedules and things like that. So things to discuss. Have a great weekend, folks.
Thank you.
Max Kostecki to the counseling center. Max Kostecki.
You're welcome. Take care.
Shay Gordonson, Jack Mango, Aiden McRory, Dan Zimmer, Gingy Jenner, Jackson New, Evan Calvez, Angelina Cerami, Lauren Fernandez, Lucia Geiner, Connor Jenkins, Gabriella Centrillo. Please come to the office.